Hey guys, welcome to Unit 9 Notes D. Today we're going to look at enthalpy as it relates to phase changes, and we're going to look at a specific type of heat called the heat of formation, another type of enthalpy. So it's all about phase changes first. And if you remember, it's pretty easy to calculate heat using the specific heat, Q equals mc delta T, but we've only really used this equation with one phase of water so far. We've also never used it for a change in state or a phase change. We have looked at using calorimetry to solve for that, but today we're going to look at another type of equation. When we are using Q equals mc delta T, the C, of course, is our specific heat, a definition we've seen several times now. The thing you have to be careful about is that it is very specific, hence the name. So if you have a different phase, you would have a different specific heat. This is not just the specific heat of all H2O. The 4.18 joules per gram degree Celsius was only for liquid water. If you have ice, you would change the C to 2.09 joules per gram degree Celsius. And if you had steam, it's actually 2.03. So you want to be careful that you use the specific heat of the specific substance. That being said, we still can't use any of this with the phase change. So what do you do if there is a phase change? What if you're going through melting and freezing or condensation and vaporization? What are we going to look at instead? We want to know the heat per gram. This isn't now dependent on temperature. You may remember the phase change graph had those plateaus. Actually, let's go back here. These plateaus indicating I am adding heat, but not getting a temperature change. That's because the heat energy is being used to weaken or break the intermolecular forces instead. Conservation of energy, right? It can only do one or the other. So although there's not a temperature change, there is heat being added, and we need to know how much energy that takes per gram. So first we're going to look at something called the latent heat of fusion. Latent pretty much means hidden, which is kind of hidden because it's not having a very obvious temperature change. And then heat of fusion is going to indicate that those particles are getting closer together as they freeze, they become solid. So we've got our heat of fusion here of 334 joules per gram. This is how much energy is required to cause the phase change per gram. It is going to have a different sign though, depending on what phase change is occurring. If we're going from solid to liquid, the particles would need to move faster, meaning we would need an input of energy. So my heat of fusion would be positive. But if I'm going from liquid to gas, if I'm going from liquid to solid, those particles now need to get closer together, meaning they have to lose energy. And so this would be a negative 334 joules per gram if we're talking about the freezing process. Positive if we're increasing the energy of particle, negative if we're decreasing the energy of the particle. Same amount of energy, but you just have to consider whether it's being exothermic or endothermic. And again, endo is always positive and exo is always negative. So that's going to apply to this part of the graph. When we are going through a phase change, we have the heat of fusion, delta H, with the subscript FUS to indicate it's the heat of fusion, as opposed to we'll have heat of vaporization. We've looked at heat of reactions or solutions. This is heat of fusion. But that is energy per gram. So you're going to need to multiply that by the mass in order to get the total amount of energy. So the Q for this section of the graph would be delta H times the mass. And you just got to be careful that you give the delta H the correct sign, so your Q ends up with the correct sign. Now let's look at the other phase change. If we're looking at the phase change between the gas and the liquid, we would have the heat of vaporization, an enthalpy change for how much energy is required to change the phase of 1 gram of the substance. Notice this is a much higher number, and it refers to the higher part of the graph. Here we're going to use our delta H of vaporization, but again, that is the energy per gram. So if we multiply that by the mass, we can get the Q for this section of the graph. How much energy is required total per mass? If it's this much energy per gram, times the grams will give us the Q. We just again have to be careful of the sign. If I'm going from liquid to gas, I would need to input energy, and so that would be positive. But if I'm going from a gas back to a liquid, I would need to release energy, and therefore this would be negative. And that will therefore dictate your sign of Q. The mass can't be negative, of course. So those are our two new formulas, more or less. Now I want to apply all of these things to a big problem. I want to know the heat released as I take a given mass of 250 grams. I'm going to cool it from 125 degrees Celsius all the way down to negative 40 degrees Celsius. So I'm going to go through all 5 sections of the graph, and I need to make very deliberate choices. Which delta H do I use? Which C do I use? What is the temperature change for that section of the graph? When do I use delta H versus C in the MC delta T formula? So these are all things we have to think about for each separate step. This is going to give us a total of 5 Qs. In order to get the total amount of heat to go through all of these steps, we have to add the steps. So we're going to be basically finding 5 Qs and then add them up. So let's start at the beginning. First thing I need to do when I have 125 degrees Celsius gas is cool it down to the change where it starts to go from gas to liquid, which we know occurs for water at 100 degrees Celsius. During the phase change, you can use Q equals MC delta T, but you have to be very careful to use the C of the steam. Because I have the C of the steam, I want to look at the delta T of going from 125 degrees Celsius down to 100 degrees Celsius, only looking at that temperature change of 25 degrees Celsius. I'm going to handle the other parts of the temperature change in the appropriate sections. For this section of delta T, I'm only looking at the change from 125 down to 100. And this is the most common temperature that's messed up, the most common mistake in the gas temperatures. People forget to take out the 100 degrees that we're going to look at when we look at the water. So this delta T is only the 25 degrees. We'll use the C of the steam instead of the liquid water, and the mass will be the same for all of them. Now, if you look at the second step, we're going to go through this phase change here. So this is where you're looking at the delta H of vaporization times the mass. Make sure you're using the vaporization for the vaporization section of the graph and the heat of fusion for the freezing and melting part of the graph. So up here, we're going to use that big number, the 2,260. It is going from gas to liquid, so it's going to be a negative 2,260. Then the next section of the graph is to cool down the liquid water. So we've made it now this far, time to go down the liquid water. When it starts this cooling down of the liquid, it's at 100 degrees Celsius, and the next plateau, or the next section, is at 0 degrees Celsius, which will be the temperature where the liquid is turning into the ice. So during this temperature, or during this phase, I would only have the delta T of that 100. And I'm going to use the C that I'm used to for the liquid water. And again, the mass is the same. Once we've made it all the way down to the freezing point, we want to look at the energy to actually freeze it. So that would be our heat of fusion as a function of the mass, and it is negative because it's going from the liquid water into the ice. So the particles must lose energy. Then we're finally going to get to the end of this curve, and we need to cool it down to negative 40 degrees Celsius. When we were at 0 degrees Celsius, and we need to drop another 40. So the delta T I'm going to be looking at there would only be that drop of 40 degrees. I do want to be careful to use the specific heat of ice and then multiply that by the mass. So we're thinking very deliberately. When can you use the specific heat? When can you use delta H? Which ones do you use? So notice for the phases themselves, the steam, the liquid, and the ice, that you're using the MC delta T formula. For the phase changes, steps 2 and step 4, you're using delta H's. The vaporization process, or the opposite of that being the condensing process with the opposite sign here, is using our delta H of vaporization, whereas the melting and freezing would use delta H of fusion. You just got to be really careful about your signs. So let's plug these numbers in. First, our heat of steam using the given mass, the specific heat of ice, and the difference as we go from the final temperature of 125 down to the initial temperature of 100 would give me this negative 12,700. Then if I look at m delta H, given the mass with this negative delta H of vaporization, we get a negative 565 joules. Using Q equals mc delta T for water, using water's specific heat and the temperature change going from the final minus initial, so it ends at 0 from the 100. So we get the negative 105 joules, 105,000 joules. And then m delta H, using the negative delta H because it's losing energy, we get the negative 83,500 joules. Can't read today. Then for our ice, we're back to using mc delta T during the phase itself as the ice cools down, dropping the temperature of 40 degrees Celsius. So it ends at negative 40, started at 0. So again, we have a negative answer here, being careful to use the specific heat of ice for this step, negative 20,900 joules. And now that I have the the Q for each of the phases and each of the phase changes, I can total that energy up, leading to a total negative 787,100 joules. Huge number, so a lot of answer keys and books and stuff you'll see will go ahead and convert that into kilojoules, which will be negative 787.1 kilojoules. So the idea is to make very deliberate choices for each of the Qs needed and then total them in the end. Let's look at one more example where we're not going to have all 5 phases, or all 5 stages, I should say, so that we can think about what phases are necessary, what stages are necessary. So in this question, we want to know how much heat is required to bring this given mass of water that's at 45 degrees Celsius up to 100 degrees Celsius and then vaporize it. So one trick that I like to do is to kind of sketch out the phase change graph, knowing that this would represent my 0 degrees Celsius, oops, did not line that up, and this would represent 100 degrees Celsius, and try to use that to figure out where I am on the graph given the question. So it says I start at 55 degrees Celsius, which would be somewhere in the middle of the graph, and then I want to go up to 100. So I'm going to go from the 55 up to this 100. So it's the liquid phase of water that we have there, which is going to use Q equals mc delta T, where C will be the specific heat of liquid water, and delta T would be the change just between the 55 and the 100. Then there's another step it asks about. We also want to vaporize it, which would be getting to the end point over here, going from liquid to gas. So it would be the positive delta H, and the delta H for the top plateau was the 2,260 joules per gram. So that means I'm going to use Q equals M with the delta H of vaporization, where that number is positive. I'm going to need to find both of these Qs and then add them together. I don't need a Q for ice. I don't need a Q for any kind of melting or freezing. I don't need a Q for the gas itself because we didn't even go past 100. We stopped right at 100. So there's only actually 2 Qs that we need, but we want to make deliberate choices over which specific heat and which delta H to use. So let's set this up. First, for the going from 55 to 100, you're going to be able to use Q equals mc delta T. So we've got the given mass that stays the same for all of the steps. Since I was in the liquid water between the temperatures of 55 and 100, I'm going to use 4.18. And then I end at 100, started at 55. Final minus initial is going to dictate our sign for Q. A positive, it would be 26,000 joules, which they've converted here to kilojoules. Let me write that out just so it's not confusing. 26,000 joules. And then I also want to look at what it takes to vaporize, so going through that actual phase change. So M, again, same mass, but the delta H we're going to use here is this positive 2,260 joules per gram, which would be 306,000 joules total. Then I want to add these two up to get our total energy, which is 332,000 joules. Again, joules are a very big number, so a lot of times you'll see that converted to kilojoules, but if it doesn't specify, either one is fine. So you have to know which steps to do and then add them together. And that's our enthalpy through phase changes. A little tedious, but it is the same idea over and over again. You just have to be really careful with your choices. All right, let's look at the next concept, the next type of enthalpy we're going to study. So this is something called the enthalpy of formation, which is exactly what it sounds like. Enthalpy representing the heat energy and how much it takes to form a substance. So we're going to look at the change in enthalpy between the reactants and products, and we're always going to look at this during standard conditions. So you may remember STP from Unit 7, but standard conditions for thermodynamics actually have a different temperature. It's going to be 25 degrees Celsius, but it is at least still 1 atm. So at 25 degrees Celsius, which is relatively close to room temperature, and 1 atm, which is your normal pressure at sea level, you're going to be able to compare how much energy it takes to form different substances. So, a couple things to note about enthalpies of formation. Usually, it is exothermic. It is more stable to form a compound, and so it would release energy. Not all, notice this is usually. There is a table, which I'm going to show you here in just a minute, that has the delta H of formation for every single type of molecule. You'll notice that the enthalpy of formation for an element that already exists naturally is 0. Example of this would be like a solid metal or a diatomic gas. Well, these things already exist, so how much energy does it take to make something that already exists? Well, none. And therefore the enthalpy of formation for oxygen gas, for example, or just pure copper, for example, those things take no energy to form, they already exist, and so their enthalpy of formation would be 0. What we're going to be able to do is take the reactants and products and compare their energies to determine if the reaction to form the product would be releasing energy or absorbing energy, and how much energy that would be. So this is about what the table looks like. You're going to have not only enthalpy that we're discussing today, but also something called Gibbs free energy and entropy on this table. So one thing you want to make sure you're doing today is that you're reading from the delta H column or the enthalpy column. We're not worried about the delta G or S columns quite yet. The other thing you want to be really careful of is that you have the exact substance. For example, hydrogen gas and the hydrogen ion have different enthalpies. Liquid water versus water vapor would have different enthalpies. So you want to make sure that you find the exact substance in question, and that's the number that you're going to use in the calculations. So what does the formula look like? In order to find the total enthalpy of a reaction, I want to add up all of the energies of the products, and if I have multiple moles of products, I would add that up 2 or 3 times, whatever the coefficient is. I also want to find the total energy of the reactants, and again, consider the coefficients, so I have the total amount of energy. And then I'm just going to do product minus reactant. So this looks like one of the craziest formulas we've seen, but it really just simplifies down to product minus reactant. So let's look at an example. The first thing that I would do is cross out things that have a 0 enthalpy of formation, because what does adding 0 really do? Here I have a pure metal. That's going to take no energy to form. That already exists. An ion, however, would require energy, so these two won't be 0. And then over here I have, again, a pure metal, which already exists. So I'm going to go ahead and mark out the solids because I don't require energy to make them. What I want to compare is the energies of the aluminum ion versus the copper ion. But notice that there are coefficients. So that's going to act as kind of a multiplier on our enthalpies. So I want to find the total amount of product and subtract the total amount of reactant. So if I look at the aluminum, look that up on the table there for aluminum, I would need to multiply that number by 2. And if I look up the copper number on the table, I'm going to need to multiply that number by 3. And I can tell that because of the coefficient. I have 3 coppers, so find the copper number, multiply it by 3. I have 2 aluminums, so I'm going to find the aluminum number, multiply it by 2. So when I do that, I need to make sure that when I do get those total, I take the product and subtract the reactant. So you can do this as 2 separate steps. Find all the reactants, find all the products, and then do the subtraction. So 2 times my enthalpy for my product of aluminum minus the 3 times the enthalpy for my reactant, the copper. These numbers came from that big table that we just looked at. So we would look up exactly aluminum 3 plus, plug in that number and multiply it by 2, and we look up exactly copper 2 plus and multiply that number by 3. Now we just got to be really careful about order of operations so that we end up with the correct sign of negative 1,256.4 kilojoules. Quick side note, the coefficients are exact numbers. They're not going to limit sig figs. They're essentially a shortcut of adding. This entire thing is a giant addition problem, and so you want to make sure that the decimal stays. So if each of these have 1 decimal, then my final answer should have 1 decimal. You go by least decimals for significant figures. All right, let's look at one more type of question they could ask you. Here we want to use the same idea of heat of formation, but this time it gives you the delta H of the reaction. This is the delta H of the entire reaction. So then the question is actually, what's the delta H of the benzene? And if you look on the list, the benzene is not listed. So this is actually our unknown. What is the energy of the benzene? So we can still set this up as delta H total equals the delta H of the product minus the delta H of the reactant. Before I start looking up numbers, let's get rid of things that are 0. Oxygen gas already exists naturally. That's going to be 0. And so let's go ahead and cross that out, which is good. Now we don't have to worry about that 15 halves or 7.5 moles of oxygen. What I do want to look up is my carbon dioxide's heat of formation and my water's heat of formation. So I'm going to do 6 times the number for the CO2, and I'm going to do 3 times the number for the H2O. Watch the phase there, liquid H2O. Pull those numbers up on the chart and plug them in to multiply, and we should be able to get the total number of the product. The only reactant that I have is the C6H6, which I don't know. So I'm going to be basically treating that like X. What is my heat of formation? I do know, though, the total enthalpy is this negative 3,267.4 kilojoules. So if we can find the total amount of products, it's basically that number minus X is equal to the given negative 3,000. So then we just got to solve for X. So let's see what that looks like. All right, so getting rid of the oxygen, the number for 6 would be the carbon dioxide number. So off of that table, the carbon dioxide's heat of formation would be negative 393.5 kilojoules. So that times 6, in addition to my water, 3 times the heat of formation of the water, which is this negative 285.8 kilojoules. Find that total amount, and we get negative 3,218.4 kilojoules. I want to subtract the heat of formation of the benzene and set that equal to the given heat of the reaction. So basically, this whole big crazy thing here is my unknown, or my X. So if I want to solve for X, first thing you would do is add the 3,218 to both sides, leaving you with a negative 49.0 kilojoules. But that's going to be equal to negative X. Notice where the sign is. So if I want to find the enthalpy for positive X, or the positive heat of formation for benzene, I'm going to flip both signs, or basically multiply or divide by a negative 1. So the enthalpy of formation for benzene ends up being a positive 49.0 kilojoules. Again, keeping the decimal consistent for our significant figures. So this is using the heat of formation table in order to do product minus reactant and set that equal to the total energy of the reaction. That's going to do it for notes D. Our next set of notes in Unit 9 is notes E, all about spontaneity. We'll see you there.